Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning. Okay, I hope you are all doing well. Um, uh, Probably it's best to your mute the what uh, mic for everybody so that we can have a clear recording. Okay. For today, even though that not that many students attended our online session, never mind. For those who are already here, I hope you can benefit more than those who are not able to join. Um, like the previous 2 weeks ago, we already have our discussion or example on the rocket propulsion. So for today, I'm going to share with you. Hopefully, I can able to share with you three aircraft propulsion examples, and together with the solutions. Right. The first question, a typical question that or problem that you will face in a aircraft propulsion problem is this particular question, right? Basically, in this example, a modern jet engine which has a temperature after combustion, right? They provide information of the gas temperature, right? At about 1,500 degrees Kelvin with the pressure of 3,200 kilopascal as it enters the turbine section. So imagine uh, the uh, the amount of gas temperature 1500 degrees Kelvin as well as the pressure at 3200 kilopascal when it goes into the turbine section. So the first turbine section that the gas or the exhaust gas coming out from the combustion chamber is it will face the turbine the nozzle guide vane. So the first turbine section is nozzle guide vane that will receive the amount of high temperature of the gas, and then it also provides us with the information of the air values at the compressor inlet, which is set at 80 kilopascal, and then at a temperature of 260 degrees Kelvin. And similarly with that, they also provide us with the outlet compressor condition with a pressure of 3,300 kilopascal with a temperature of 700 degrees Kelvin. As you can see here, the temperature from of the air going into the compressor has already rise from 200 degrees Kelvin to 780 degrees Kelvin, right? As well as the pressure also has already been increased. It's already been built up from 80 kilopascal to 3,300 kilopascal. And then when it goes out into the turbine section, right? The combustion condition has already been provided earlier. When it goes into the turbine outlet into the nozzle, the pressure has already reduced to 400 kilopascal. If you plot the temperature, right, from 260 goes to 1,500 and then goes to 780 Kelvin, and it goes to the nozzle 900 degree Kelvin and finally exit the nozzle at 640. Whereas for the pressure, it starts with 80 kilopascal, goes into 3,300 kilopascal. It is being burned at 3,200 kilopascal and goes into the turbine outlet at 900 degrees Kelvin and at a pressure of 400 kilopascal and finally goes into the atmospheric at 80 kilopascal. Okay, what you need to do in this typical question is basically to list down those information already provided. At the same time, you may be asked to state all your assumptions. So we will look at what are the assumptions normally being made to simplify our problem. Okay, and then the question asks us three things. One, to find the compressor specific work terms, and then the second item is the turbine specific work terms, and finally the nozzle exit velocity. The nozzle exit velocity is the VJ, and if you still remember our early slides on the aircraft propulsion. Right, as highlighted earlier, in terms of the station, coming from the compressor goes into the compressor outlet, and this number 3 is the station of the combustion chamber, number 4 is at the turbine, and number 5 is at the nozzle. And normally you will be given the value for the enthalpy for each station, okay, each point with the respective temperature condition. So you will need to use all of this information later on when we solve the problem. Okay. What are the assumptions, right? Normally we have a few assumptions. Some cases we have 4 assumptions. Normal cases we have 2 to 3 assumptions. So what can we assume? Why do we need to assume? Okay. In any propulsion problem, assumptions being made basically to reduce the complexity. Basically, you want to make sure that, of course, the problem is real, but in order for us to approach it at a more appropriate way, as a first guess, you may provide a few assumptions. Among other assumptions is we may neglect any heat transfer and also neglect heat kinetic energy except out of the nozzle. All right. So that's the first assumption we make. If we don't assume any heat transfer to be occur, so we have to ensure all the other parameters where along the way there are heat losses from the compressor. We can also have heat radiated from the combustion chamber and so on and so forth. So in our simplification, we neglect all of that. And then the second assumption that we can make is that the compressor, the turbine, as well as the nozzle, all right, are all steady state. Okay, and single flow devices, we treat it as a single flow devices. We neglect other than that, as well as we assume that they are adiabatic, meaning that there's no heat transfer through all of this section except for the combustion chamber, right? So you have to be able to put your assumptions if being asked. Okay, the air properties that already been given earlier, so we name it as enthalpy 1, 2, 3, 4, and 5. Okay, so make sure you have all the units correct. Make sure when you extract the information, you copy the right information for all the values. If not, you will carry the error throughout the problem. Okay, the first question is asking us to find the compressor specific work. What are the equation that we can use? Basically, compressor specific works normally denoted by symbol W, and we have a subscript C as a compressor, and the equation basically we deduct the we have the values of the enthalpy at the station 2 minus the value of the enthalpy at the station 1. So this is at the compressor inlet and the compressor outlet. If you still remember the table that been given earlier, number 1 is the compressor inlet, number 2 is the compressor outlet. So you just deduct the two values and we will get the value for the compressor specific works, which is 539.36 kilojoule per kilogram. So make sure you do not have to put so many decimal places. 2 decimal places is already good enough. Okay. Um, the second part of the question is asking us to find the turbine specific works, which is denoted as the symbol W subscript T. For the turbine, instead of using 1 and 2, we use 3 and 4. When it goes out from the combustion chamber, the value 3, enthalpy 1635.80, we minus the value of the enthalpy at station 4 at the outlet of the turbine. Okay, and you will get the turbine specific works to be 702.65 kilojoule per kilogram. And finally, you want to find the exit velocity, right? What equation you need to use? You may just use the energy equation for the nozzle, right? I simplify it to H4 equal to H5 plus the kinetic energy, half V squared. V5 is the velocity of the exit, or Vj, okay? So you have the information there, and finally you will get the value of 283.62 kilojoule per kilogram. This is for the value of the kinetic energy. And then to continue, right, you want to find the nozzle exit velocity, which is V5 or Vj. You then continue to solve the kinetic energy value, right, to get the value of the final exit velocity, which is come up to be 753 meter per second. Okay, so of course it's quite it looks simple, it looks straightforward, but make sure there are so many mistakes can be done in terms of forgetting or you simply do not paste the right numbers. The equation are quite straightforward. Normally in examination you will be provided with the formula. Okay, so just a matter of putting the right numbers into the equations. Okay, so right, that is example number 1. Okay, before we proceed, let me just stop recording.